Hello everyone, welcome to this AOS-CX 10.10 update on FIB optimization. My name is Vincent and with me is Daryl from the Technical Marketing Engineering team. So the usual agenda of the TOI, we'll start with an overview and use cases. First, some acronyms and this definition. So you have that already in previous slide deck regarding EVPI, and we're just going to focus today with the forwarding information base, which have active forwarding entries being programmed into the hardware, into the ASIC, based on the routing table. So this is all what we want to optimize in order to save space and enable higher scale deployment. So in terms of overview, let's start with what it means exactly. So all the VTEP access switch, remember this is a campus use case, all the VTEP access switch will learn host route /32 EVPN host route of all the connected devices per shared VRF. So on all the VTEPs in the fabric. So this will overload the host table of the ASIC on those access switch, as those are typically in the 6300, I would say medium, small hardware table size. So a separate lookup is done on that host table in the FIB, and the size is 49,000 entry for the 6300. So we want to optimize so that we do not consume those 49,000 entries quickly in the campus. So for that, we propose an optimization that is to program into the ASIC only the active flow, only the routed destinations that are active. And we'll do that through a mechanism that we call conversational host routes learning. We'll have, of course, an edge out timer for non-active flow. After the flow has been seen as not being active, we'll remove that entry into the ASIC. And all of that will allow us to deploy large-scale EVPN campus. So this is quite something important for a large account. So pay attention that the remote MAC is still programmed into the ASIC for stretch VLAN. In the fabric. So there is no conversational MAC learning mechanism that is available as of 10.10 right now. So, and if VLAN is not shared, obviously the remote MAC for non-stretch VLAN is not programmed into the ASIC. You will also notice that a previous name and internal name in some OVSDB column that I'm going to show you in the troubleshooting refer to Aruba Intelligent Forwarding. But publicly, we are going to use FIB optimization. Use cases are, so as I mentioned, this is mainly for campus and where we have distributed gateway across all the access VTEP that are those access switch access 1, 2, and 3 are VTEP, and with north-south traffic mainly. Right, so those VXLAN in orange, those VXLAN tunnels are the tunnels over which we'll get the north-south traffic. And obviously, we'll have a bit of traffic between those connected devices, connected clients. We'll have probably less than 20% of east-west traffic, unlike data center. So all the circuits on the layer are layer 3. Yeah? And so as before that FIB optimization, each VTEP will learn all the EVPN routes, host routes, even if there is no communication between those clients. Okay, if there is no communication, we'll still learn those routes, and I will explain you why. So the host, the ASIC host table is unnecessary program with all the host entries in the fabric. So it can quickly lead to a situation where that IP host table in the ASIC is full. So typically here on that access 3 VTEP, right, we know the local host for sure, but we learn as well the 6 or the 5 over remote host. And in that case, maybe that PC3 has no traffic at all, or that IP phone has no traffic at all to the other nodes. So regardless there is traffic or not, this is programmed. Without FIB optimization, let's consider that, for instance, this PC here, PC2, initiate traffic to the upstream server. So that PC2 IP will be learned, right, as a route type 2 EVPN, and that route will be received on access 3. This route, 10.1.10.15/32, this one from PC2, is getting programmed into the ASIC, regardless there is traffic flow on that destination or not. So if you look at the show capacity layer 3 resource, you will see there will be some entries being programmed. Okay, again, that capability for 6300 is 49,000 entries. Next, you can, with some appctl command in the shell, you can see that route entry as well as host entry. Next, with FIB optimization. So same, we start that PC here starts an upstream traffic to that server, and that route is received. ACK3 is still receiving the type 2 routes. However, now with FIB optimization being enabled, that entry is no longer programmed. So if you look at the show capacity status, you will see that the value is reduced. The consume entries is less. And if you look at the route entries in that appctl command, you will see that the entry disappeared. It's no longer listed here. So this is literally listing the IP host table entries. However, if you look at the MAC address on ACK3, the MAC address in the same VLAN, so the VLAN 12 is stretched between access 1 and access 3, that MAC address table still have the MAC address entry learned through EVPN of the remote VTEP. It does not change for the MAC address. It's just the IP table, the IP host table. So the benefit is to save host table entries in the ASIC. So how much do we save? Actually, this is a rule of thumb. Without FIB optimization, you will have a number of hosts on average per VRF times the number of VRF. This is what you will consume. With FIB optimization, as we have something like less than 20% of traffic volume east-west, and probably even less in terms of number of involved hosts for that 20% east-west traffic, literally we'll save something like 80% of the space of the ASIC host table. So this is a huge saving for a large-scale deployment. So some details and see how it works in terms of packet forwarding through that conversational host route learning mechanism. Because as the host entry is no longer learned in the ASIC, how we are going to solve that. So first, again, PC2 here as an example, initiate traffic to upstream, let's say, and so that it's not a silent host, so that this entry, the type 2 entry, will appear in the EVPN control plane. So that entry is again received on access 3. And with FIB optimization, the entry is not programmed in the host table. So now what happens if PC3 here want to initiate traffic to PC2? So PC3 initiate routed traffic to PC2. The packet is routed no longer based on route type 2, but based on route type 5. And that information is the destination subnet the PC2 is belonging to. So we've got 10.1.10.15, and the subnet is 10.1.10.0/24, for instance. So based on the type 5 EVPN route entry that access 3 VTEP has, it will push the traffic to that next stop, which is access 1 VTEP. You may say, yes, but what if there is multiple access VTEP hosting? Well, we'll cover that case one will be preferred, most likely the lowest router ID, and we'll see potential suboptimal path. So next, what happened? As this packet is forwarded based on the route type 5 and reaching a destination next stop hosting this type 5 route, we also send a copy of the packet to the CPU. And we do that until the host route entry is programmed in hardware. This copy to the CPU has nothing to do with software forwarding that the CPU would do further of copying the packet. We won't duplicate any packet. That software forward, there is no software forwarding. That CPU copy is purely to notify the CPU to take an action to program the entry into the ASIC. So after the CPU is notified, this packet is actually dropped from the CPU perspective, right? It's just a notification mechanism. So, and if you look at the COPP policy, that there is a class for FIB optimization in the COPP policy, you will actually see packet passed counter that will increment if there is no issue. And that's normal, even if the software packet that reached the CPU after the notification is actually dropped, because there is no need to re-forward that by software, as the first packet get to the destination with type 5. However, if it happens there is too many packets, let's say there is suddenly 1,000 hosts connected to the access 3 and bombarding with request for flow initialization, then of course there is a COPP policy that will protect the CPU, and the default rate is 100 packets per second. So if there is too many packets copy to the CPU to get the host entry being programmed for that notification mechanism, then we will see drops. So the outcome of this mechanism is that the host route are programmed in hardware only when there is an active traffic, an active flow. There is a daemon next on access 3 that will keep polling the status of that flow. This is called a hit bit in the ASIC to check if the flow between PC3 and PC2 is still active, right? This is a way for us to see if we still need to have that entry in that destination IP in the hardware. So if there is no active traffic any longer to that destination, I was mentioning the flow, sorry, it's not based on the source. And it's, really the hit bit is about the destination. If there is a traffic to that destination, regardless the source, on the access 3, if there is that hit bit, if we'll say there is traffic to that destination. So if there is no traffic any longer because the hit bit is not set to 1 but set to 0 now, we see that there is no traffic, then that host route PC2 here is removed from the ASIC and marked as inactive. So it means that it has edged out. So the outcome is that, as you can see, that this conversational mechanism will preserve the hardware table, will avoid to be filled unnecessary, and allow large-scale campus deployment. And this is aimed for a layer 3 VNI host route. So this is between different subnets, not inside the same subnet. So there is some caveats. First, it's IPv4 only for that release. As I already touched a little bit, we'll see some potential suboptimal path. There are some fixed pending for known issue in delay establishment when there is a stretch in the feature is enabled with a combination of stretch VLAN. We need to warn that aggregation border VTEP is not supported for FIB optimization. So you cannot enable, well, it's really not recommended to enable FIB optimization on aggregation border. I will cover that in detail. We'll talk about COPP, the border VTEP exclusion that needs to be set on the access switch. What about cascaded L3 switch as well, and point on VS6. So let's dive into those. First potential problem of suboptimal path for first packet. So again, we have no route type 2. In that example here, on access 3, FIB optimization is enabled. Only on that one, just as a matter of simplification to explain you what could be the problem. So this entry 10.1.10.15 is not programmed in the neighbor hardware table in that guy, right? And access 3 will consequently push packet. So that we already covered. The PC3 initiate traffic to PC2. The packet is routed based on route type 5 information for the destination subnet, which is that class C here. So to VTEP, access 1, you can see here, I put the subnet 10.1.10.0/24 on access 1 and on access 2. So there is 2 candidates for that destination. So it is the lowest router ID that is most likely the one that will be preferred in the BGP decision tree. So it means that it can be based on the IP, it can be access 1 or access 2. So let's assume this is access 2 as for educative purpose. Traffic is sent to access 2 over L3 VNI. A copy of the packet is sent to the CPU, and PC, let's say this entry is programmed into the ASIC. So the packet is received on access 2 and say that access 2 has no FIB optimization. So the entry is already programmed in access 2. And we have next step is that access 2 send the packet to access 1 over an L2 VNI this time. VLAN access 2 is re-forwarding the packet into the same L2 VNI as this is the shared VLAN here. So PC2 can be a silent host, and if the ARP is unknown, the packet is forwarded in as an unknown unicast packet over L2 VNI. So broadcast MAC and destination IP being PC2. So PC2 respond to the packet of PC3 to establish the TCP flow, for instance, over L3 VNI directly here. So again, I mentioned that access 1 has no FIB optimization as per the example explanation. So PC3 now, as the entry has been programmed, will send the packet to access 1 directly. So as you can see, there is a potential suboptimal path that would include additional latency to go through one additional hop. It is not so much an issue as of now. It's an extra micro or 10 microseconds in addition to the packet, and it's just for the first packet. Consider that FIB optimization is an optimization mechanism, so it does not cover all the niche case where it's not entirely optimized. But we consider that this use case is a regular nominal use case that do not necessarily impact much the campus traffic. Now, FIB optimization and stretch VLAN. So exactly the same scenario. You want to have traffic initiated from PC3 to PC2, but this time you enable FIB optimization on both, and you have for the destination, for the source traffic, so PC3 as inside VLAN 12 here. The same VLAN 12 is, and the same subnet is also hosted on access 1. So we'll see that in that condition, we found some specific known issue that leads to an additional establishment in delay in establishing the traffic. So let's go to that one. So same use case than before. Traffic is sent to access 1. Let's say that this time we are lucky it's not going through access 2, it's going directly to access 1 as a matter of simplification of explanation, and the copy of packet and then programming into the ASIC. However, as the packet is reaching access 1 as the return packet is for that subnet. But that subnet is also hosted as an SVI on access 1. So it means that it's local. And as this is local, it's preferred. So the packet is not pushed to access 3 VTEP because that entry, 12.16, is not yet programmed in access 1 hardware. So in that particular case, we have to optimize the way that it is being the logic, the software logic to make that entry being programmed. And we have right now 1.6 second traffic loss. And again, there is a fix that is being integrated now in the current branch of 10.10, but that will appear in maintenance releases, probably in June timeframe. Another caveat is about aggregation border. So this one is as designed and needs to be clarified. So if FIB optimization is enabled on the border, which should not be the case, but let's say as a purpose of explanation that it is enabled, any traffic to an external destination will be reported to CPU for programming the host route. However, that host route type 2 does not exist for that destination that is external to the fabric. It knows that only through type 5. So the route optimization does not make sense because there is no type 2 to be programmed there. So first of all, it does not make sense. And if it is programmed, then as there is no type 2 routes, the software copy for the packet will try to program something, and it will lead to a lot of drop in the CPU copy without any effect. So that's not recommended. Huh? So on the border, so typically the aggregation layer is the border for the campus fabric. That border should not have FIB optimization enabled. Huh? It's not recommended and not supported. So in the slide deck, in the speaker note, there is a Jira ticket that is documenting those caveats. So feel free to get into this, and you will see that it's as designed. Another caveat about COPP and the COPP drop, and as well what needs to be done in terms of border VTEP exclusion, this time on the access switch. And also, what about a layer 3 switch that would be cascaded behind VTEP? So first, for COPP, at each flow initialization, there is again a copy to the packet to the switch CPU. If there is too many packets that gets copied to the CPU, just to trigger the mechanism to program it in hardware, it will first be reported as a drop. And there might be some, in each case, it can trigger an avalanche effect that as those host routes are not yet programmed into the ASIC, they will be the mechanism will keep sending a copy of the packet to the CPU and so on. So this is something that in campus should never happen, but if, for instance, customer would enable that in the data center, we will have to take care and you will probably see drops. So something that needs to be known for the support. Next is what I talked already about is what about external destination? So if there is a flow initialization to a destination that is external to the fabric, no type 2, only type 5, it will end up by packet already copied to the CPU, and that will never end, right? So we need to make sure that the border VTEP must not be configured on access VTEP and for that, we have an exclusion command. So we'll see that in the configuration of the command. We have a way to exclude a next hop for FIB optimization. So any host entry that comes from a particular VTEP as a next stop will not be optimized. So it means that it will be programmed if it needs to be programmed. So typically that route type 2 would exist if we have, for instance, inter-fabric communication, right? If we've got traffic to an external host that is in a VRF underlay, for instance, then there is no type 2. And next point is about cascaded access switch. So imagine that there is an access switch that is a layer 3 non-VTEP access switch that you cascade behind an access 3. There will be no type 2 EVPN entries that will appear on that VTEP here on access 3. And consequently, you may have exactly the same situation where you have a lot of packets that are not programmed into the ASIC because simply the entry does not exist. So that use case is not supported. Now the VSX use case and the potential impact. So reminder for VSX use case in that context. So first of all, FIB optimization is not recommended and not supported at aggregation. So that use case, you will recognize that I switch aggregation switch name by access, right? So those say that being aggregation, we know that already FIB optimization should not be here. But imagine this is an access. Remind that the poor access authentication is not synchronized between VSX peers. So this we consider this use case is not so common in the campus as an access use case. What we have is due to the hashing, let's say server 1 want to send a reply packet to a laptop or PC behind that access 1. So due to the hashing mechanism on that server 1, we that MC lag, that access 4 receive the traffic. Okay, so send the traffic. So that access 4 has programmed already in the hardware the destination for PC1. Let's assume that there is a link failure. So the traffic will immediately go to the second link on access 5. That access 5 have not yet programmed because there is today no synchronization of hardware hostable entries between the VSX peers. And we do that on purpose because, again, that is an optimization to save space. So there is no reason to unnecessarily consume space in the VSX peer if the flow is not going over. So that packet is sent again on access 5 thanks to type 5 routes, destination subnet. So it could be access 1, it could be access 3, it could be access 2, if this is hosted on access 2 as well. So let's assume this is access 3 that is chosen. We already see that sub-optimal path. So the packet is pumped to the CPU for programming in hardware. So the packet reach access 3. Packet is broadcasted over VLAN 12 and associated L2 VNI and sent to access 1. Packet is reaching access 1 and forwarding to PC1, and the return packet is going over, and then the next packets will go from server 1 directly because of that that hardware entry being programmed to the destination. So you understood it. Now, although that FIB optimization again is not supported on aggregation layer, we qualify that for the VSX acting as an access VTEP in case some customers are using that. But again, that should not be so common. And the impact that we see for link failure on that host, for instance, is less than 1 second. Okay. The platform supported for that feature are 6300, 6400, regardless V1 or V2, and 8360. So there is an API available for FIB optimization, so you can get the status of FIB optimization with the response body, and here you've got as an information the schema for programming the config. Then you have the COPP as well, which has an API for a class that is called FIB optimization, and as well if you want to program the burst rate and so on. And finally, some statistic that you can see as well through API. For configuration in the CLI, it's very simple. You have FIB optimization. Then you will use EVPN VXLAN, and then you will say host route. And then that's for IPv4 only for that first release of the feature. We have now that command to enable here as a summary, and obviously to disable, you will perform a no. So when that feature is actually active, when it's get programmed in the CLI. So there is two cases. Without clear BGP, if you enable that as you already have some EVPN routes, you have to wait for the edge timeout, that is by default 90 seconds, before those entries are removed from the ASIC. Right. So if you test that feature and you enable, you will see that right after enabling, you still have the entries after the default timeout. Those will be reset. If you do a clear BGP, those routes will immediately be optimized and not programmed into the ASIC. Default timer, as I mentioned, is 90 seconds. You program it with FIB optimization edge timeout. Yeah, some notes about should I reduce or not the timer? Well, you may say, well, I am going to put a very small timer because, I'm going to free up very frequently that hardware table for any non-active flow, right? But if you've got flows that are, if you've got hosts that start and stop periodically and in a time period that is close to the edge out timer, that might consume a bit more CPU for all those entries. So I would recommend to keep as a best practice to keep that 90 seconds and to smoothly increase or decrease that based on the COPP that you are seeing, the COPP statistic. There is a protection, so it's really deep dive here. There is an internal mechanism for edge out host entries that are a lot of entries. For instance, imagine that you have suddenly a lot of entries that needs to be removed from the ASIC. Then we will proceed in batch in order to make sure that the CPU is not impacted by removal of all those entries for communicating over to the ASIC that it needs to be removed. Configuration for exclusion, as we mentioned, the border must be excluded. So here, the exclusion is on the next hop. So you are going to exclude with that command, FIB optimization EVPN VXLAN exclude next hop. Here you will put an IP that is not the destination IP of the host route entry that you want to exclude from the optimization, but the VTEP that is the next hop. So the EVPN routes that you received as a VTEP next hop, and this is that next hop that you will put in the exclusion list if you do not want that those corresponding EVPN routes to be optimized. So they will always be programmed into the hardware. You can remove that, and that is not only one IP. In the command you can have multiple set of IP address for next hop. So obviously, if you put some next hop here, those corresponding routes will be immediately programmed into the ASIC. So, and yes, in this release, this has been something that we already discussed internally. In this release, we do not have the possibility to exclude a destination host. Okay, it may come later. We do not know yet. VS6 as a way to for the configuration to synchronize the FIB configuration, the FIB optimization configuration. This is nothing to do with the synchronization of the state that the hardware has been programmed on. This is really just a matter of configuring the feature. So some best practices. So for campus, it is recommended to enable it when there is no or little east-west traffic. I would say typically less than 50%, let's say, okay, of east-west traffic, then you enable it. If you've got a lot of clients participating to east-west traffic in the overlay, so then disable FIB optimization. Again, it can be counterproductive to do that because you will have to a lot of edge flow will edged. You will have to reprogram, so you may see some CPU increase, and then you will have some drops and so on. So really, it's an optimization for campus nominal case where there is no or little east-west traffic. The default edge timer, keep it, it's 90 seconds. Use the next hop exclusion for identifying next hop. So typically, that is the border VTEP, okay? And this is what I mentioned here. In the data center, do not use FIB optimization. If really you have to, because you want to limit, it means that first of all, you need to pay attention that there is no east-west, not so much east-west traffic. And if it's really something that you have to enable, pay attention that the COPP policy drop must be really seriously watched. And obviously, sub-optimum traffic path may be seen a lot as in the symmetric IRB distributed gateway. You may have the VLAN stretch on and hosted behind multiple VTEPs. So really not a good use case for data center. Troubleshooting, we have a show FIB optimization. So just to check that it's enabled or disabled, you have a time, the edge out time that is mentioned here, and the list of next of VTEP that are excluded. Here I have none. As well, you have a show IP route FIB optimization per VRF, where you see the list of hosts that are optimized, so that are known as type 2, but not yet programmed in hardware. And you have a summary, keyword summary, if you want to have just the number, the count of those routes. So there has been some discussion about if we should have that such a command or include that in the show IP route without FIB optimization to show with a flag. So stay tuned. There might be some change in the future about that for ease of usability. Show IP route FIB optimization for the traffic that is edging. So here I will go through a typical process of what if the flow is active and then edging. So here on that access switch, I will do a check on that destination. Okay, so you can see that it's known here. And then as this is in the FIB optimization report, it's optimized. So let's say the traffic is initiated by some connected host to that destination. So then in that show IP route FIB optimization with 10.1.10.15, the F1, that route will disappear. So it means that it is not optimized, it is programmed in hardware. Next. Traffic, let's imagine the traffic is stopped to that destination. Okay, so you still do not see any optimized because you have the timer. And after, so traffic is stopped for a time that is longer than the edge out time, you will get back that, that information into that command. If we do a show IP route, which include host routes, so this is something that can be perceived as misleading, but again, we'll work out that in the future release, that you can still see those /32 in the IP routing table. Okay, so they still appear here, even if they are not in the ASIC. So to have further input and if you want to dive into some appsTL command for the layer 3 resource manager, you will see with that command here that you have the AEF, so that's the other name that I was talking about. That's the flag and status for is it optimized or not. You will see inactive. Okay, so that entry is inactive, meaning it's optimized. So from that table, it has been derived that show IP route FIB optimization, just to explain you the genesis of that new command and where it comes from. Okay, so from those inactive, you will see with that option in show IP route the optimized entries. COPP, before active traffic, you will see a counter here, and after the traffic is starting, after a few packets, you will see that the COPP is refreshed, the statistic is refreshed, and you will see increase of the packet passed. So normally you should have no drop. Huh? Again, the drop would be drop if the CPU is, there is too many load on the CPU for CPU copy, so that the CPU is not finally notified that an hardware entry needs to be programmed. It's not at all a packet that is dropped. It's the copy of the packet to the CPU that is dropped. And now I will hand over to Daryl for a demonstration.
Okay, thanks, Vincent. So this is my demo topology, demo environment. We'll be focusing on the access 6300 number 4. Let me show you the switch. This is what it is. And let me show you before and after. Currently, FIB optimization is disabled. And I'll show you the resources. Currently, we want to focus on the IPv4 neighbor entries. Right now it's 44. This is before optimization. Next, I'll optimize. So this is the command. FIB optimization, EVPN vextend, host route IPv4. If you do a check again here, now it's enabled. But take note, when you first enable it, it'll take some time. The entries will not be optimized immediately, about a minute or so. And then after some time, you see that value go down. And you see those routes in here. So right now, there are no host routes optimized. So let me go back to the topology to explain further while we wait for that. So we're here. We also have a host here, 12.16. Let me show you that. You can see here, the host IP address is 12.16, right? From here, 10.1.12.16. Okay. Basically, we also have another access VTEP on the left with multiple hosts here on different subnets, 12.15 and 10.15. We also have a northbound server at the data center where we have tunnels. So assuming the campus, majority of traffic is north-south, we should expect routes north-south to be normal. Right? Those will not be optimized, but east-west, that's minimal east-west traffic. So those routes should be optimized if there's no communication between these clients. So that's what we'll see later once we have enabled this optimization here. Right? So we should see those routes be optimized. So now we can check. Go back here. Let's see. Okay, now you can see routes have been optimized, 22 routes. We want to focus on like 10.18. That's here, the top. Right now it's optimized because there's no traffic. Let's take a look at the resources. What changed? It was initially 44. Because we turn on optimization, it's now 22. So 22 resources are used in hardware. Okay. So that's the difference. And let's say we generate traffic now from this host now to the server, up to the server. We should see a resource go up being used. So let's generate that traffic. Ping to 10.18 from 12.16 to 10.18. Let's generate that. Stop it. We should now see the resource increase, right? Because it's being used in hardware. So that resource is now additional, one more compared to 22. If you check the FIB optimization route table, you should see 1018 disappear because it's no longer optimized. It will not show up here. And that value also from 22 down to 21. Okay, so that's north-south traffic. After some time, because I stopped the traffic, that 1018 should automatically come back in. It's dynamic. The switch will monitor traffic. If there's no traffic, it will be optimized. So 1018 will come back in after some time. So let's look at east-west next. We have 1015 and 1215. That should be here. 1015, 1215. They're both here. They're both optimized. Okay. So it will be optimized whether it's on the same subnet, on 12 subnet or a different subnet, 10 subnet. So it will work for both L2 and L3. You can see that. So let's see again if it came, if that 1018 route is now optimized. Still hasn't, right? Take some time. Okay. Another thing we can do is to prevent optimization of host routes. So let's say we expect lots of east-west traffic between these two access VTEPs. So we can actually disable optimization by adding a command here. So you want to exclude, put this command. Exclude the next hop 2.5. So you can see 1015, 1215, they're using 2.5. It's the next hop. So that means when we add this, all entries with this next hop will be removed. It will no longer be optimized because we expect that traffic between those access VTEPs. But before we do that, let's check again if that 1015 has come back. Okay, 1018 has come back. So you see, because there's no traffic, it's automatically optimized by the system. And we look at the utilization, see 22. So there are 22 entries being forwarded in hardware now. Next, let's do that next hop command. Here, you want to exclude that. So 2.5 will be removed. Okay. Once we do that, you should see the routes, the hardware resources also go up. 27 now. Of course, we shouldn't see any routes next from 2.5. So all the 2.5 routes are now being forwarded in hardware automatically. Okay, so with that, hopefully you understand more about the feature. I'll stop sharing. And I will back to Vincent. Thanks.
Thank you very much, Daryl, for this great demonstration, which really helps in understanding the feature in details. So thank you for that one. You will find more resources in the next update of the VXLAN user guide. And with that, this concludes our session on the FIB optimization. Thank you very much.